Okay, hello everyone, and welcome to the very first of the National Atmospheric Chemistry Seminar Series talk. The entire idea of this seminar series was to try and get people interested in atmospheric chemistry to talk to each other a little bit more, and also for everyone to be exposed to some of the latest research that's happening in atmospheric chemistry in India. In fact, when I first sent out this email asking people whether they would be interested in this, the response was overwhelmingly positive. And it also just showed how much interest and how many experts there are working on atmospheric chemistry in India. This is really encouraging because this is a field that is growing rapidly. And of course, there are lots of questions that we still need to answer. And we know that these questions will help improve our forecasting for climate and also for weather in certain cases. So the idea of the seminar series is not just to get experts who have done great work in the past to talk to you all, but also get experts who are actively working in the field to present some of their latest research. So not only students, but even advanced researchers have an idea of what the rest of the community is doing. And hopefully that can lead to some collaborations and more exciting work in the future. With that very short introduction about the National Atmospheric Chemistry Seminar Series, I'm going to invite our very first speaker, Professor Chandra Venkataraman, to give the inaugural talk as a part of this series. Before I introduce Professor Venkataraman, I'll just mention a few quick house rules. The first thing is, yes, we are going to do this series once a month, and there is an email list. There's a form link, which I'll put into the chat later. If you can fill out that form, you will get updates about the seminar series. We promise not to spam you. You'll just get the link for the seminars and the announcements for the seminars as they happen. The other thing is the seminar series are not supposed to be one-way talks. We are hoping that these are discussion events, and which basically means that everybody who has a question is more than welcome to ask a question. And even if not a question, if you have a comment or a point to make, or you can think about some way your research can contribute to the topic, you're more than welcome to speak up. We'll give Professor Venkataraman about 30 minutes to start with, so she can introduce her topic and talk about some of the work that she's doing, and then we'll have a discussion session. If you have a point to make, my request is raise your hand so we can invite you to unmute your mic and ask your question. Or of course, you are more than free to type it out in the chat window so that we can ask the questions. And the only other thing I'll ask is towards the end, I'll ask you all to put on your video cameras so we can take a small photograph with everyone there. With that, I'll stop this introduction of the series, and I'll introduce Professor Venkataraman. Professor Venkataraman, she is based at IIT Bombay, and she's a professor at the Department of Chemical Engineering over there. She's been working on climate sciences for a very long time, but that's not all that she does. In fact, the group, as I understand, they have a motto which says they aim to use aerosol sciences to serve society through a diversity of environmental to medical applications with a very strong local relevance. Considering this, she's been doing a lot of work on aerosol sciences. Quite a bit of her work has been on observational laboratory experiments, trying to get new emission inventories for aerosols prepared. They do a lot of modeling work, including regional models such as WRF-CAM, etc., to national models such as ECAM and HAMOS. And in addition to that, what they're doing is they're trying to understand the feedbacks between aerosols and climate and weather also. She's not only working on aerosols from a climate perspective, but also I see from her website that they have been doing a little bit of work on nanoparticles for drug delivery, which is an interesting linkage with the aerosol sciences, which us in the climate sciences community do not really think about a lot. Uh, Her past education, basically she was educated at IIT Delhi, where she did her BTech, and then from there moved on to do her MS in Alabama, after which she did her PhD at UCLA. And then she came back to India and has been working on climate sciences, and in fact has been one of the lead scientists working on aerosol sciences for over the last few decades. She has helped her found the interdisciplinary program in climate studies, which is based at IIT Bombay, which has been producing some of the lead scientists in aerosol sciences over the last few decades. She's a fellow of the top academies in India, which includes the National Academy of Sciences India and the Indian Academy of Sciences and the Indian National Academy of Engineering. She has more than 100 publications, and that list could go on, and has also produced more than 20 PhD students over her career so far. Having said that, it's not that these are all past achievements. She's still very actively involved in several projects which are funded by various organizations, including the Ministry of Earth Sciences and the Ministry of Environment, Forests, and Climate Change. And some of the work she'll be presenting today is a part of that. With that short introduction, I invite Professor Venkataraman to share your screen and please give us your talk.
So thank you, Anup, Dr. Mahajan, for this all too kind introduction. And good afternoon, everybody. I hope you can see my screen and also hear me.
Yes.
Okay, great. So today I want to talk about, I also wanted to appreciate Dr. Mahajan for really organizing this series. And I think he put the idea very correctly across that it really is giving us then a opportunity for collaboration, an opportunity for interaction and so on. So in that spirit, I'll talk about interdependence of aerosols and climate chemistry, forcing and feedback. So, and now my slides don't go forward, so I'm going to try to, okay, there we go. So it's well recognized that the composition of the atmosphere, largely greenhouse gases, aerosols, and other trace species, are drivers of climate change. So they're drivers of climate change because they interact with radiation. What's shown here on the left is the IPCC AR6 plot, which shows that we have an observed warming from pre-industrial to present day of the order of about a degree Kelvin, degree Celsius. And then that breaks it down into different chemical constituents of the atmosphere: carbon dioxide, methane, nitrous oxides, some of the CFCs, HFCs, halogenated gases, etc., etc. By the time we come to aerosols, there are sort of two big ones: organic carbon, which is shown as blue, which essentially implies a cooling, and black carbon, which is shown as brown, which implies a warming. Both black and organic carbon are largely anthropogenic in origin. About 65% or more of black carbon arises from energy use activities. So that is different fuels, whether we're talking about chulas or whether we're talking about diesel engines or coal-fired power plants. While the remainder arises from open biomass burning, agricultural fires, grassland fires, etc. Now, as models go today, organic carbon is largely represented as a scattering or a purely cooling species. However, over the last couple of decades or so, the community that deals with the optics of aerosols has identified a fraction of organic aerosol which is absorbing of radiation, and this absorption is spectrally variant. It occurs very strongly in the UV vis and then tails off, while in fact black carbon spectral absorption is much stronger and is spectrally invariant. So then with that introduction, dust is not here in the IPCC list, but has some level of absorption. So we have black carbon, brown carbon, as we name the absorbing organic carbon, and dust as absorbing species. And we know that climate change is linked with the frequency of extreme events becoming more likely to occur. And what is shown is that high temperature extreme events or heat waves over here um, will have become about 3 times more likely to occur in present day compared to pre-industrial, and may, in the different warming scenarios, 1.5 degrees centigrade or 2 degrees centigrade by 2100, they may become 4 to 6 times more important or more frequently occurring, and there are high risks, including mortality, human mortality, impacts on the ecosystem that arise from heat waves. And if we then look at the inverse question, which is, yes, we now understand that atmospheric constituents are forcers of climate. What happens if there is radiative feedback or climate change feedback? How would it change air quality? And this slide just basically says you have absorbers and scatterers, which we've already talked about, and the scatterers being many of the inorganic aerosol species, nitrates, sulfates, ammonium, etc., etc. This alters the temperature structure of the atmosphere. It can change stability, it can change, reduce downwelling radiation, it can change surface temperatures. And because of that, it also alters the atmospheric chemistry in terms of the reaction rates and the kinetics of the atmospheric chemical reactions. So here, this is just to point out that air pollution is a very important problem in India, third leading risk factor to premature mortality. And in fact, the northern states are, as we all know, are very highly affected. When we look at the evidence on heat waves, we find that observational studies are basically pointing out an increasing frequency and an increasing duration, both the mean and the maximum duration in Northwest India. Other regions are North India and what's called North Central India are also affected by heat waves, as well as a belt in Eastern India in the Andhra Pradesh region. Attribution studies are telling us that the changes in the hot extremes lie outside the expected range of natural variability, which means that there is an anthropogenic driving component to it. And heat wave mortalities are significant. Now, there are various factors that are linked to heat waves, meteorological factors, and of course, atmospheric composition. And meteorological factors include North Atlantic blocking, or which is linked to an anticyclonic high pressure region in North India over here, leading to less cloudiness, descending air, leading to heating and leading to maybe even lower soil moisture, etc., etc. And the Eastern India heat waves are related to anomalous cooling in the Pacific. So there are sort of what we call large scale atmospheric features, and greenhouse gases have been associated with the increases in the number of heat waves. However, aerosols, specifically aerosols in many other parts of the world, are associated with surface cooling. The reason they're associated with surface cooling is that aerosols would, whether they absorb or scatter radiation, reduce the amount of downwelling radiation, as has been pointed out. But does that always lead to only a cooling of surface temperature? So when you have a scattering aerosol layer and it scatters back radiation, it cools the ground below. It also cools all the other layers because it's not allowing incoming radiation. However, when we have an absorbing aerosol layer, this is going to heat up the layer in which it resides while it cools the lower layers of the atmosphere. So one of the questions that Ban Weiss asked in an idealized simulation study in 2012 was, if we take black carbon and inject it at the surface, 0 kilometer or up to 5 kilometer, what do we see? And what they saw in the modeling study was a positive response, an increase in surface temperature. And when the black carbon resided very, very high up in altitude, which is 12 to 30 kilometer, largely because of the amount of energy radiating out to space. It resulted in a surface cooling. So we have a mechanistic understanding that absorbing aerosols can lead to a positive response in surface temperature, and they've been shown in other studies to offset scattering aerosol effects. Um, I want to point out this equation here, which is looking at the change in surface temperature with time and the different balances, the different terms in the surface energy balance are the net downwelling radiation flux, watts per meter square, the latent heat flux, the sensible heat flux, and the ground flux. So we'll talk about this in detail as we go through the talk. Okay, once again, I have a problem here. Okay, all right. What is different about Indian region aerosols? What's different about Indian region aerosols is that we tend to see a smaller predominance of inorganic scattering species. The sulfates, nitrates, etc., shown in the left panel shows Schneider Messer et al. It's a very nice review of atmospheric chemistry, air quality, and climate, a bit dated now. But they're basically showing that sulfates, nitrates, etc., can be a large part of the aerosol in other regions, but however, in India, they're a smaller section. We see mineral dust. This happened to be in ocean region, the area that was taken out of the simulation. That's why we have a lot of sea salt, but that's not true continentally. But we have a large amount of black carbon, organic carbon, and mineral dust. In other simulation studies, David et al. And which we participated in and our own study here, we're seeing that anywhere between 30 and 50% of aerosol optical depth is contributed by organic and black carbon, green and black, and dust, which is pink. And that is very significant because organic black carbon and dust are not as hygroscopic. The more amount of water these inorganic aerosols, which are the sulfates, nitrates, take up, they grow to kind of wet particle sizes that will really, really strongly lead to optical effects. But even with that, we have very large burdens of the carbonaceous and dust species. And then when we come to the surface, we're looking at a pair of simulations here, microgram per meter cube. There we clearly see yellow organic carbon, blue, black carbon. Very, very significant parts of the surface aerosol is composed by carbonaceous species. So carbonaceous aerosols and dust predominate in the Indian region, and we want to understand how they will moderate air quality and climate. Typically, the methodology that we use is to start with statistical studies to extract correlation and causal relationships of aerosols to different climate variables, whether we're talking about rainfall, whether we're talking about temperature, and then do modeling studies to explore physical causality and the underlying mechanisms. We used both general circulation models and regional climate models, and for different purposes. When we want to run long-term simulations, we use the general circulation models. When we want to look at event by event kind of time scales, or a year type of time scales, regional climate models give us higher resolution. So we run ECAM, HAM, as Dr. Mahajan has said, and we run WRF-Chem with certain chemistry and so on to be able to ask these questions and answer them. Coming to the first study, this was a study led by Prashant Dave, and we had a long data set of 1979 to 2013. That's 35 years of temperature maxima as well as absorbing aerosol index. Why use absorbing aerosol index? Absorbing aerosol index is a measure, it's a satellite product, and it's a measure of column absorption. So it is more sensitive to higher altitude aerosols. However, it would be a reflection of the amounts of black, brown carbon dust, especially that's there in the atmosphere. So we wanted to look at the trends in this. Two different regions, Northwest India, Central India. I'll come to why. And in Northwest India, of course, there's been a almost continuous increase now, and this is for the hot season, March, April, May, June. While at the same period, the aerosol index has been increasing as well. And then the question was, do we have a relationship between them? And what Prashant did was he made a cross correlation analysis that essentially asked, would for any pixel in Northwest India where I have a daily Tmax value, and this we were looking at anomalies. So the daily Tmax anomaly in that pixel, which is the difference between that day's value and the 35-year mean. And what correlation then does it bear for that entire 120 days? Does it bear any correlation to absorbing aerosols, AAI, anywhere? And what he found was a very interesting result that said that increases in Tmax in the Northwest were linked not only to aerosol index, so correlations of the order of zero point 0.5 or so, and that is the local effect. But Tmax went up in North India when absorbing aerosols went up in Central India, and that is the non-local effect. So this was done on a seasonal basis as well as on the 2-week, 10-day, 2-week type of heat wave event scale. So we showed this correlation. But as we know, correlation does not imply causality. So statistical testing of causality was done with using Granger causality. So it poses the problem like this. It says maximum temperature anomaly on a day, let's call it T, is related or can be explained by absorbing aerosol index T minus I, that is on preceding days, and the maximum temperature on T minus J, which is preceding days. What are I and J? I'm sorry, so I goes from 1 to L, J goes from 1 to M, and these are the lags. So we're asking today's maximum temperature, does it bear a relationship or is it being explained by yesterday, day, lag 1, lag 3, lag 5, all the way up to lag 11? We found different influences. And this is, of course, the unexplained part here, epsilon. This is called the unrestricted model, and the restricted model takes AAI out of the equation and says that today's maximum temperature anomaly or change is explained only by previous days' temperature changes. And if you're able to prove statistically that the variances between this unexplained part, the difference in variances between the unconstrained and constrained model is much lower than the variance in the in the constraint model itself, you're showing that AAI has made a difference to the prediction of the maximum temperature. So what is shown here is an example. What was found was in those 35 years, there were 9 years where local causality, AAI Northwest to Tmax Northwest was found. And for 11 years, non-local aerosol causality, which was AAI or absorbing aerosol in Central India caused. And this is a causal effect. And what you see over here, of course, is the lag adjusted plots. So if you see the AAI blue going up and the Tmax blue going up together, where it illustrates the case. And the top row is local And I'm just showing 3 of the years, though it was found for 9 years, and we're showing 3 of the years for non-local, which is found for 11 years. So now we have evidence that Indian region aerosols essentially lead to increases in temperature maxima, particularly in the heat wave region or the region susceptible to heat waves. So then we move forward and ask the questions. Um, what is the underlying mechanism? Can we see this in models? Can we explain it physically? So here we used simulations made with the CAM6, HAM2, GCM, and these are 1971 to 2010. And the approach taken very quickly was to look at a hot composite, the 10% of um, the top cases or top months in the Tmax anomaly distribution and compare them to the rest of the 90%, which is called climatology, and try and identify what was the difference in the model between the hot composite and climatology. What we essentially found was in the hot composite, we had smaller single scatter albedo, that is, the surface aerosols were far more absorbing. And if you remember Van Weiss's study, black carbon, of course, is the most absorbing. Here we have a mix of aerosols. I should probably take a minute to say that ECAM HAM has the Hamburg aerosol module represents aerosol microphysics. It includes all the species. It allows for an interaction into what is a mixed aerosol, so that aerosols don't exist as individual species. So the mixture and the optics of the mixture is simulated in this model, which was a good reason to choose it. And whatever it was, it led to a very absorbing nature of this total aerosol. It's not just black carbon or dust, but the mixture itself. And that led to a higher shortwave heating rate forcing. Interestingly, the ground was hot. It had very little moisture and a large amount of heat coming off the ground into the surface air. And because it had very little moisture, there was very little evaporation. So you had what's called sensible heat flux increasing and evaporative cooling decreasing. So all of this is, further illustrated here. I also want to say one thing, which I forgot to say, which is that, the large scale features that were found in the observational studies that said that, you have a subsidence, you have enhanced geopotential height, you have reduced relative humidity, very clear skies, low soil moisture, all of that was also shown in the model. And so the large-scale meteorological effect found by other studies was preserved in the model. And then we showed in addition an aerosol effect, which is really heating several Kelvin per day, enhanced heating in the hot composite compared to the climatology. And the reduced latent heat flux here, positive is actually a reduction because of the sign convention used, and an increase in the sensible heat flux. So now we have understood a little bit more in terms of a mechanism of how, at least in the model, and it's also consistent in terms of physics, can aerosols or a mix of aerosols indeed lead to an increase in surface temperature. This is just a quick slide to show that we used the evolving aerosol and a low aerosols pair of simulations to kind of look at how temperature changes. This is delta T, which is the T aero high aerosols minus low aerosols in the Himalayan regions, and found statistically significant increases alongside increases in black carbon and the same essential way of heating up of surface temperature. But that also then drove snow melt in Western, Central, and Eastern Himalaya. And we're basically finding that the number of snow melt pixels in the evolving case, red is larger than snowmelt being positive in the low aerosol case. In both cases, of course, there were pixels with significant snowmelt, but we're just showing a greater frequency or incidence. Now, I think given the constraints on time, I think we'll just skip some of these slides which say how we optimize the model. We do use meteorological data assimilation here, but the data assimilation constrains the large-scale meteorology, but it allows for aerosol feedback to take place. I'll also skip this, which is model evaluations, which show AOD evaluations, PM 2.5 evaluation, chemistry evaluations, and temperature evaluations. I'd like to just point out that IMD and as well as model, we're looking at many cases where 44 to 46 degrees centigrade temperatures were present in the observation, were simulated in the model. And then, of course, cases, regions where it was a little bit lower. So despite the fact that, we have different definitions of heat wave, we want to show that the model and the measurements are, and the model is able to capture the measurements. So we had a pair of simulations here. One called base simulation. I'd like to say here that, the model does have GHGs and they are the same in both cases. These were simulations made for 2015. And in the other simulation, which was no ARI or no aerosol radiation interaction, we switched off the direct effect of aerosols, whereby either the heating or the cooling takes place. And asked the same question about whether or not aerosols are heating. So what we found over here in 2015, and I'm showing the simulation, the animation is going to show the difference in Tmax between base and no ARI, which is the aerosol radiative effect induced increase in temperature from May to June. So we had seen that in 2015, the really, high heat wave time period was from 20 May till about 10th of June. And we do see very interesting features in the model in that what we call dry heat stress or the increase in T max is shown throughout the period about 23 May to about 5 June. But relative humidity increases. And here I should say where blue is above green, we say that's an aerosol effect. That is the base minus the no ARI. And so there are two periods here where moist heat stress, the increase in relative humidity shown in red, and the increase in wet bulb temperature shown in red. And we're trying still to understand what might be the mechanism in the moist heat stress enhancement. And once again, during the high dry heat stress period, we show the enhancements in T2 max can be of the order of 1 to 3 degrees centigrade here on the left with, similar sort of enhancements in black carbon. There are many positive ones during the ARI-induced heat stress period. So we see consistency in these different model studies about what to do, what is the aerosol effect. So quickly, last topic. When we have aerosol radiative feedback, what does it do to particulate pollution? So the way in which the question was asked in this modeling study was to turn on and off the aerosol radiative effect. You can ask the question differently by making future year runs which show climate change effects and emission effects separately. Here, the same emissions were used and only the radiative feedback effect was looked at. The mechanism, which is well known in literature, is that the aerosols lead to a reduction in surface downwelling radiation, an increase in temperature where they reside. Therefore, increases in stability, reduced vertical mixing, sort of a pressing down of the boundary layer. And we saw all of that here. If you see surface shortwave radiation, surface temperature, and the planetary boundary layer, what we're really looking at is these amounts in the base case, and all the changes are in the negative direction. So decreases in planetary boundary layer by 50 to 100 meters. So that is really our meteorology effect. And what did it do to the PM 2.5? This is our typical base case PM 2.5. It's an annual mean, so some seasonal features are not here, but you see the north-south gradient, you see the whole Kharif biomass burning signal over here, you see the power plant signal over here, and so on, right? So with this, we find a very regionally asymmetric increase in pollution. We may argue that the increase is only 6%, but we're talking about our own national standard of 40 microgram per meter cube being exceeded a lot. And then we have further increases in PM 2.5, and they are basically seasonally even higher, and they may even go from 15 to 40% with a 30 microgram per meter cube increase. So these are all, strong increases in an already bad situation. And we want to ask what caused the increases. So the primary species, which are black, organic carbon, and dust, they contribute about 50 to 60% of the total PM 2.5 concentrations in our region. This is quite different from other world regions where the secondary species, sulfate, nitrate, ammonium, secondary organic carbon. Okay, I'll mention here that this particular version of the model, which was Radon 2 photochemistry and sorghum secondary aerosol formation chemistry, didn't give us correct secondary organic aerosol. That's why we don't have it as a species here. So we see these increases in the primary, largely from the meteorological effects. And there are some very interesting unanswered questions with the secondary, where sulfate concentrations, which is yellow, showed a reduction in summer, monsoon, and winter, but an increase in post-monsoon, where actually, for reasons we still haven't fully understood, post-monsoon which is oxidant levels, hydroxyl, ozone, and H2O2 were all higher in the post-monsoon in the model simulation. And ammonium nitrate showed the typical, increase in winter and in the region in winter as well as in post-monsoon, where you have lower temperatures and higher relative humidity, while it showed decreases in the others in summer, where essentially you have a partitioning back into HNO3 and ammonia gas. So we have some insights into atmospheric chemistry, and what we found as a very interesting result was anywhere from 10 to 20% increases in PM 2.5, which is essentially happening in very populated regions of India. We did a mortality calculation and found similar increases in mortality in these areas. So that this is of concern. So these are the final conclusions. I think I'll let you read some of the conclusions at the top. I'd just like to say something about the fact that we have some very interesting science to do. We've barely scratched the surface on what really is happening, what is the penalty that climate change is going to impose on air pollution, both ozone and particulate pollution levels, the mechanisms. Other than that, there's another interesting question which review papers have raised now, which is that climate change is going to lead to land use, land cover changes, and is going to uh, change biogenic emissions of VOCs, which are drivers of biogenic organic aerosols. So, this is also something which hasn't been explored in the Indian region. There's a lot of work to be done. Once again, we may like to explore where the coincidence in time and space of air pollution extremes and heat stress may impact vulnerable populations, how much will they affect it, etc. So that's all. Thank you very much. And thank you for listening. I'm happy to take questions. Back to you, Anu.
Thank you, Chandra. That was a wonderful talk and shows how aerosols are essentially contributing to big changes that are happening not just over India but also globally in terms of radiative balances and feedbacks. With that, one quick reminder: we are monitoring the chat, so if you do not have access to a microphone, feel free to type in your questions in the chat window, or of course raise your hands, and then we'll welcome you to ask your questions or your comments directly. Uh, while people are doing that, Chandra, I had a couple of very quick questions for you.
Yeah.
Uh, the first thing is you see a pretty clear signal in terms of changes in Tmax because of aerosols, and that seems to be uniformly around, and mainly because these are because of BC, so absorbing aerosols. Would a similar effect be seen on T minimum in places where you have more sulfate aerosols, for example? Would you expect changes in the minimum temperature rather than just the maximum?
So, that's a very interesting question. What we find with many studies that are, currently be reporting aerosol reductions of temperature, they are really talking about mean temperatures. Okay. So the way that temperature maxima behave and the way that mean temperature behaves seems to be different, because in our simulations as well, what we found was somewhat of a reduction in mean temperature, but we found a very clear signal, and also it seems to be a time scale. If you're going to average mean temperature over seasons and so on, you're always going to see an aerosol cooling. But if you start looking at temperature maxima on daily scales, that's when you start seeing the aerosol heating. So it's something we haven't yet looked at minimum temperature, but that's an interesting question that you ask. And I think we'll have to look at it again. I mean, in terms of an aerosol mixture, as to when we may have the T minimum getting further driven down. I think it's a very interesting question. I don't have an answer to that right away. Yeah.
Right, yeah, because it's interesting. Right now, we are obviously worrying more about the absorbing aerosols over India, but as we start cleaning up our emissions,
Yes.
we are going to see a bit of a change. And as you rightly say, the assumption is, of course, that aerosols are helping mask some of the global warming that we are seeing. But what you're showing here is it's might be helping with the mean, but with the T max, it's a completely different story, right?
Yes. Yes.
Okay. The other thing I had was you showed that very interesting figure over there talking about how the vertical positioning of even black carbon
Hmm.
can affect whether it's cooling the surface or heating the surface. And of course, there are lots of people who have been thinking about using aerosols for geoengineering, and it's always focused on sulfates or iodine aerosols, etc. But is this an indication that you can even use black carbon for it?
Well, I will, say that my philosophy would not be to put out pollutants into the atmosphere. My philosophy would be to control whatever we are putting out. But that said, the effects are all fairly non-linear. And of course, when we're talking about the temperature effect and that stratospheric sulfate can lead to surface cooling, I think the same sentence should say what it does to our monsoon. If it turns off our monsoon, we're not in business, right? So I think that some of the things that, when we're looking at one variable, but not the other. And of course, aerosols are implicated very much in, rainfall perturbations. So I would say that we need to be really, really careful if we're talking about geoengineering experiments.
Yeah. So it's interesting you mentioned monsoons over there because there are indications that aerosols do play a pretty important role in terms of monsoon. Now, there are dual effects. One is, of course, the long term, like seasonal or multi-day effects, which is the mean temperature matters more. But since you're seeing a change in T max, would that time short time scale feedback have an effect on monsoon or precipitation, according to you?
So even with rainfall, um, yes, now it's very well accepted. IPCC 6 has also increased the confidence level on aerosol suppression of seasonal mean rainfall. But what it does to rainfall extremes is still, a question that is quite open. And there are, the way it modifies clouds with aerosol, invigoration of clouds can lead to increasing the intensity of wet spells, but you can also increase the duration and the frequency of occurrence of dry spells as these spells are defined. And so I think that you could be intensifying certain type of drought type situations. I think Manmeet Singh has a very interesting paper coming along from IITM Pune as well. And one could also at the same time be looking at the role of aerosols in cloudbursts in intense rainfall events and so on. On the temperature feeding back to it essentially needs to be accompanied by some convection change, because the moment you have the higher temperature, if you have enough moisture in the ground, you're going to have an increased and moist static stability. So you're kind of filling up the atmosphere with a lot of water vapor, right? But if that water vapor is sitting right there, it's not going to result in a catastrophic rainfall event. Something has to push that water vapor up and then make it into like a drastic cloud. And so you need the convection to drive it. And I'm not sure whether, we're showing an increase in stabilization during these events. So I'm not sure you'll get a convection accompanying uh, any increases in moistatic energy close to the ground. So we'll have to see.
Okay, fair enough. There's a question from Yang Lian who's asking,
Yeah,
is the mineralogy of dust considered in the simulations, like hematite-rich dust
yeah.
are more absorbing than others? Which also brings me to a larger question is, in the models, you obviously have to simplify things. And for composition also, you simplify things a lot. How much effect do you think, not just dust, for example, but SOA, there are different types of SOA. There's, black carbon is not only by itself, but it can be coated by other things.
Yes.
So how much effect in terms of composition of different types of aerosols do you think is going to have on the simulations that you make?
So hello, Yang. Nice to see your question. As Dr. Mahajan was also saying, essentially what the model does is for each of the aerosol species, it will assume a refractive index. And the refractive index of dust has a small, what is called imaginary component compared to, let us say, black carbon, which has a much larger imaginary component. But we're talking about multiple effects. And the ECAM-HAM model does combine the refractive indices of all the the components and create a mixed aerosol, and therefore an effective refractive index of an aerosol containing multiple species. It sometimes holds it has one fraction which it holds as non-hygroscopic and one fraction as hygroscopic. So one of the fractions also grows quite a lot in size with water, the other fraction does not. So it's more a question of if the black carbon happened to be mixed with dust and somehow happened to be hygroscopic. So there is one soluble species mode where dust and black carbon can mix, that would contribute the most in this model to the absorption and to, all these effects. So yes, models can't go to the level of detail that we can with measurements, but they answer, some very important large scale questions, of course. Yeah. And Anoop, I forgot your question. You said?
No, it was along the same lines,
Yeah.
talking about composition. How big a role does composition play, rather than just having 4, 5 individual types of aerosols, because they
Right.
can
No,
be a
now
mixture,
I
right?
think almost all the models have moved away from what is called an external mixing um, idea, where you have black carbon sitting separate from dust, sitting separate from sulfate, sitting separate from nitrate. They all use some way to mix it up and have it in different modes of different sizes. So, what exactly is the amount of mixed and amount of soluble, and all these different models have different assumptions. The other question you asked, what happens when black carbon is coated with scattering species? That is, some models use what's called core shell optics. They put in the ME program that calculates absorption. They will have a black carbon and dust core, which is absorbing with the organic carbon and the aqueous species as a shell. And that does increase factors of 1.5 to 1.9 or so, the absorption, the radiative forcing, and all of these, and the heating effects. Because of lensing, the sort of shell acts as a lens. It captures the radiation and focuses it onto the core.
Mhm. Okay,
I
that's
think,
interesting. So, hello.
yeah.
So, yeah,
Vijay
that
has a
is, yes,
question,
Vijay
I think.
Kanavade, who's at University of
Yeah,
Hyderabad, as you must know,
Hyderabad.
no?
Hello, Vijay.
So he's asking, in the atmosphere, we have a cocktail
Ah,
of aerosol chemical species, as we were just talking about. How does the model consider the mixing, internal and external, of different aerosols when looking at aerosol temperature relations?
yeah, so pretty much along the same lines, which is both MAID, which is the aerosol module of WRF-Chem, which is a moment-based aerosol module, and HAM, which is Hamburg aerosol module, are driving the microphysics. They do have multiple modes, and they do mix the indexes using these mixing rules, which are typically volume weighting of the refractive indices. It creates some problem because volume weighting sometimes increases the absorption of the absorbing species. The most physical representation would be a core shell representation, but neither of these models have the option of a core shell representation.
Thank you, Chandra. One more question I had was, all the radiative impacts that you're showing for aerosols, they seem to be more through either direct radiative impacts or through things like, modifying clouds, etc. Is there any role that these aerosols have in terms of changing reactive chemistry, gas-phase chemistry, for example, ozone, etc.? And how much of an impact would that have on radiative forcing, which is not related to direct radiation changes?
I think these are very, very interesting questions. What we've seen, of course, so far in the literature is simulations that are looking at pulling out the effect of climate change, which means the temperature, as well as anything related to wind, solar radiation, all that change, versus the emission change on atmospheric chemistry. There's a lot of very interesting work on ozone, which is there in particularly other world regions. There's perhaps only one study that's looking both at ozone and particulate matter. In ours also, we looked at both, but we didn't have enough insight, so we didn't put too much of an emphasis on the ozone. I think that there's a lot going on there, and in India we should probably unravel the ozone story a little bit, and then maybe be thinking of other things. But I'm sure people like Vinayak Sinha have more ideas on things like that, and yourself perhaps, maybe Suvarna Fadnavis. I mean, you're the people who typically have those kinds of insights. Yeah.
Yeah,
Um,
no, it's very interesting that side because we still have a lot of keeping that aside, Praful has a question which says that in the AOD calculation in the model that you've used, do you consider only aerosol mass concentration impacts on AOD or aerosol mixing states as well? Because aerosol mixing states can also affect AOD.
Correct, correct. So we use whatever is the model's default mixing state, and that mixing state is what takes the refractive indices of separate species and then puts them together, right? And then, of course, the hygroscopicity then pushes the size of the particle. And depending on where you are in the entire me scattering regime, by the time you get to particles close to half a micron to a micron, which is in the peak of the me scattering, I think you end up getting the biggest scattering sort of effects. So we do not do any sensitivity simulations related to changing the aerosol mixing state. We haven't looked at how a different mixing rule might affect our results yet. I think it's possible. One of our collaborators in BARC who uses NICAM printers, I think has the ability to do that. And actually, we haven't taken a very good look at ECAM as well. So we should be looking at that in the future, but no, we haven't done that yet.
In one of your first few slides, you showed that the OC concentrations are pretty large over India, no matter which area of the country you're looking at. But what's the story with SOA over there? Wouldn't they contribute to OC, and how right are we in
Yeah,
terms of
yeah.
SOA?
So, that was an ECAM ham simulation, but ham doesn't have HAMOS. And we're not using the photochemistry, so we were not calculating the SOA there. And then when we ran Wharf Chem with the fond hope that we would now be able to calculate SOA, we found that Radom 2 Sorghum was not doing a great job. So I think Sujit Maji is exploring other aerosol chemistry um, to see maybe Mozart VBS or some other kinds of chemistry in WorfChem to see if we can do a better job on SOA. So far, no luck with SOA.
Yeah, that's one of the big unknowns, unfortunately, isn't it? And also
Yes,
limited by observations around India, because one of the things we see is, for example, the Megan emission inventory that goes completely off in India in quite a few simulations. You really have to tune that quite a bit. So maybe
I see.
that's a good area of research for the next generation also
Yeah, and
to get
we
into.
can discuss that offline, maybe
Sure thing.
even with Sujit. We're definitely interested.
We've got a question from Shavani Banerjee who is asking,
Yeah.
we also experience nighttime temperature rise during heat waves. So is there any relationship between nighttime heat waves and aerosols?
Yeah, so this is a very good question. This whole idea that perhaps heat stress is not just to be looked at during the day, but we have to look at it during the night, because if you don't have the reduction in temperature or the reduction in relative humidity sufficiently during the night, then you have unrelenting heat stress, which can be a really big health problem. This is definitely something that we would like to look into, day and night effects separately. And it wouldn't be so much a um, immediate direct effect, because solar radiation is there only during the day, the aerosols are there, but it would be some feedback, and what we would be looking for is a long lasting feedback. So it's something that happens during the day, altering perhaps, let's say, relative humidity through the night, and keeping it high, and so on. So yes, very interesting. And there's many PhDs to go. So lots of
That
nice
is true.
ideas.
But yeah, it would be interesting to see also the memory of the system in terms of the feedback of aerosols. That's a very good question, actually. We've got
Yeah.
another question from Nandakumar SK, who has started off with complimenting you on your talk, which I completely agree with.
Thank
And
you,
his question
Nandaman.
is there any other way to separate marine aerosols, which is personally of a lot of interest because we are doing a lot of work on marine emissions.
On marine
So would
aerosols.
this would be an interesting question to ask. So
Yeah. So sea salt is an online, it's generated online in models. So if you wanted to be studying marine aerosol effects using models, what you would do is you can turn dust off and on, you can turn sea salt off and on. They are, both species that are generated with online parameterizations. If you wanted to isolate the effects of the marine aerosols, then you would look at least one pair of simulations, one with the marine aerosols on and one with them off, and then see what's going on.
yeah, but I wonder whether besides sea salt aerosol, things like DMS or your
Yeah,
organic emissions from the marine
yeah.
environment, does that have an impact over India, or is it relatively minor as compared to your continental emissions?
Well, ECAM, for example, has all the DMS reactions. I haven't looked at WRF-Chem carefully, but I think it does too. The DMS to sulfate chemistry. Organics, I haven't paid yet attention to the literature, so I think what you're saying about plankton emissions that are related to organic aerosols. I haven't looked at the literature yet.
Yeah, I mean,
Yeah,
so far, at least from the work we are doing, it seems that it might have relatively little impact directly in terms of contributing to continental aerosols. However,
yeah.
they can have impact in terms of radiative forcing and teleconnections, which might affect things over India. At least that's the
Oh,
feeling that we are getting. We have another question from Gaurav Govardhan, who's here at IITM, and he's
yeah.
asking, do you think volume weighting would give more leverage to bigger particles like dust or sea salts, and thus a more scattering nature a nature of the mix?
So actually, what volume weighting does is the following, Gaurav, which is, like I said, core shell is the best geometry. You have a tiny, typically shells are, of reasonable thickness. So the idea is that a core might have a diameter, like a black carbon core might have a diameter of 150 nanometers. And then you'd have a shell thickness that can even go up to a factor of 3, right? So what really volume weighting does is it takes the absorption that lies in the central part of the particle and it mixes it into the whole particle. And actually, what that does to a me calculation is that it increases the absorption in the whole particle. And so volume weighting tends to increase um, absorption, and it increases, the warming effects. So I think regardless of the fact that sea salt or dust or something may be larger particles than black carbon, the volume weighting leads to an effective refractive index, which has an absorbing component and distributes that absorption throughout the larger particle. And in fact, it estimates more absorption than it should. 1.5 to 1.9 times was, the typical range, and more heating than having a core shell optical model.
Okay. We've got a comment from Vinayak, who's saying, it's a
Hello,
wonderful overview
Vinayak.
talk. Great start to the National Lectures series, and thanks for highlighting the role of ozone and biogenic VOCs in a changing climate too. With that, since we are almost out of time, I'm going to ask you a couple of questions and then finish off. And these questions are related to what we are going to do in the future in this field. So, first one is, what, according to you, are the big questions that we need to start answering over the next 1 decade?
Um,
Of course,
Over
in
the
this
next
topic.
decade, right. Um, I think that we really need many more studies on when and where there is going to be heat and cold wave type links of aerosols. I'm not so much the broad atmospheric chemist. So, I mean, definitely we need more people looking into that. We need to look at whether, we're seeing those effects regionally through maybe other types of measurements. If people have long-term measurements of, and there are people who've been making long-term observations of black carbon, long-term observations of dust, and so on. So you have an actual in situ aerosol measurement, and you're looking at, temperature in any case is very well documented, and try to look for as many locations and what the variability across locations is, and so on. So far, our studies have been limited to satellite proxies. So I think moving to in situ measurements would be very good, and whether or not it is one or other type of aerosol, et cetera, et cetera. So I think that link to temperature change is sort of it's begging to be looked at in our system. The other thing, of course, is the chemistry part, a lot related to, what is the climate penalty on air pollution in our region? I actually do feel that it's likely that, emission changes rather than the climate penalty is going to control future pollution levels. And we have to say that today because we need to start cleaning up. We know enough to clean up and we just need to get the job done. So in that sense, I will say that. But the exciting science is in, what is the climate feedback to air quality, both in terms of ozone, in terms of uh, aerosols. Then the chemistry of secondary organic aerosols is just so poorly understood. I mean, even like you're saying, getting them right between model and measurement, and getting, consolidating as many measurements as you have and trying to look at it across model and measurements is the first job, right? Then you ask, is the model getting it right? What do I need to do to tweak the model to get it right? And then, I don't know if this is going to come from observational studies. There's probably a lot of organic aerosol mechanisms in the region. Secondary organic aerosol, as well as, what the huge primary organic aerosol, once it gets into, with aerosol water around it, what it does or it doesn't do to further organic aerosol formation. There's a lot of exciting, chemistry to be done related to photochemistry and secondary organic aerosols. So I think that's a lot. And again, I mean, we're always talking about the fact that we have extreme values of even mean air pollution in terms of PM 2.5 is very large. But, if you're looking at extremes, then that's another interesting thing. And as, Vinayak was saying, and as you were saying, as we start cleaning up, we definitely want to look at how biogenics change, what's happening to ozone, et cetera, et cetera. So there's a lot to be done.
So I'm going to end it with what I call as the 10 crore question. Suppose you were given a fund for 10 crores, what exactly would you do with it? Because this is essentially the younger people and in the audience, that's what they'll be doing in the future. So what would you invest that money into?
Right. So, two or three things. One is I think we need to have public consolidated data portals. Unless we all agree to donate our data to and get all our agencies to agree that we need that as a basic tool to drive science, that's what we're hurting with. So one big thing, of course, would be to have yes, data should be of equivalent quality. Yes, data should be measured the same way, and all of that is fine. But just having data in a single format and data which includes multiple locations, time series, whatever, in a single place is going to really aid science. So that is one thing which I would say. And the second sort of thing I would say is it's important to do things in a measurement plus modeling framework. I don't think that we should either we do it collaboratively, we do it whichever way we want, but I don't think we really want to be overdoing only measurements, doing only measurements in one location, or only running models and not knowing whether we're getting it right or not. So, two things. One is, of course, data portals. Second is if we could have, combined modeling and measurement studies. These are really important for our region.
Yeah, it would be great if we get all the active groups to do a field campaign together and then have the best modeling groups, model that data. That I think would be a great thing to have in the future. There's one
Absolutely.
quick question from Rajmal who's asking for the mortality estimation due to PM 2.5. What level of uncertainty do you think comes because of not accounting for different levels of toxicity of component species, but rather just using PM 2.5 as a whole?
Okay, I'm not the health expert. You should ask that question to Sagnik Day. But what I understand from reading the literature is that so far the accounting of toxicity is has like too much uncertainty, which is why the community has continued to stick with PM 2.5 exposure concentrations, the whole thing, without saying is the PM 2.5 organic, is it carcinogenic, is it inorganic, is it dust, is it black carbon. But I think there's some interesting new results. So Ramshi Chowdhury is also another person to talk to about this, that black carbon and organic carbon could have higher health related outcomes than PM 2.5 as a whole, is some of the papers that Saramshi Chaudhary has put out and so on. So there's some evidence building in that direction.
Great, Chandra. Thank you so much. I think we are unfortunately out of time, but I could keep on asking questions, but I'm sure we'll get another chance in the future. Uh, I'm sure everybody here will join me in thanking you for a wonderful talk, and I'm really glad that we managed to get you to do the very first of this seminar series, which hopefully will continue for a long time. Thank you for not just getting the talk to give us an overview of things also, but sharing some of your latest research, which sounds pretty exciting. And hopefully there'll be some new exciting results coming in the near future too.
So thank you, Anup. I really appreciated the discussion. I think the discussion went very, very well, and I'm just hoping that the entire series will also lead to that. And as you say, opportunities for collaboration and future exciting science. So thank you very much, and I'd like to thank everybody who stayed through the talk and asked questions. Great to interact with everyone. Thank you.
Great. Thank you, Chandra. Thank you, everyone, for coming. Our next talk will be advertised through the email list fairly soon, but it will be happening next month as we planned. Thank you for
Okay.
coming and
Bye.
goodbye.
Sir,
Sorry?
you want to take a snapshot of our
Oh, sorry.
Ah,
Yes,
yes,
I
yes.
completely forgot. Thank you for reminding me.
uh,
I'm just going to allow for everyone to share their cameras. Yes,
ma'am,
I
can you
think that's
please
all.
unshare your screen, please?
Oh, yes. Sorry about that.
Thank you.
Is that okay?
Yes.
Yeah, that's fine. Can I request everyone to please put on their cameras and show us your beautiful faces so we can take a quick picture before we move off? Okay, I can see a few more cameras coming on.
Yeah, and your camera is off.
Okay, I'm just going to do like some very quick pictures if I can figure out how. Okay, yeah, one. Let me just take a few more.
Oh, that's nice. Large gallery.
Yeah, I think that's it's an easy, wonderful. I know there are a few more people, but unfortunately we can't get everyone. This is the maximum number that I can actually get together, unless there is another mode. Oh wow, okay, this is interesting. All right, great. Thank you so much for this, and I'll see you guys at the next talk.
Yeah, thank you.
Bye
Bye.
bye. Padmakar, can you please switch off the meeting?
Yes, sir. Sure.